Okay, let's start today's lecture. So today we are going to learn software complexity, and this is today's outline. So we will be learning different levels of software complexity. And you may see that, okay, we have three different levels, and you don't, but we will learn about the details of how do we determine each level in the next week. For this week, you just need to know that, okay, unit level is roughly function level, and integration level is more like a combination of different functions. And system level is just like the entire system, but you don't need to worry too much about how do we determine like what is a unit, what is part of the integration. We will learn about how do we determine the level in the next week. So let's start today's content. So first, we are going to learn software complexity. And you can see the keyword here is complexity. And you might have encountered some sort of complexity metrics before, right? When you learn algorithms. So in algorithms, we learn different complexities, right? We know that different algorithms are associated with some sort of metrics for calculating their complexities. So, for example, for different searching algorithms, we can have time complexity, right? Which means that how much time do we need to run the searching algorithm. And we also have space complexity, which is related to the memory consumption of the algorithm, right? And you may also find these notations when we learn the algorithm complexities, right? This O1 means that it is a constant complexity, no matter like how large is the search space, the time or space consumption is like a consistent value. And ON means the time and space consumption is growing linearly as the search space grows, right? So this one means it's like exponentially growing. So this is algorithm complexity. However, it is different from what we will learn today. So what we will learn is not about how it's not about how long does it take for the software to run something or how much memory would be consumed by the software. What we care about today is the complexity of the structures of the software themselves. So this is what we will learn. And the complexity we have learned in algorithms is also known as computational complexity. And what we will learn is software complexity. So let's explore the differences between these two types of complexities furthermore. So for computational complexity, we just know that, okay, it is like kind of a theoretical measure of like the time or space consumption, right? It cares about the the growth of the complexity according to the, like the inputs, and is used for analyzing the efficiency of the algorithms. So this is computational complexity. However, for software complexity, we care more about the code, the actual structure of the code. So it is it is useful for us to understand how like the effort for understanding the software or modifying the software or maintaining the software. So it is a different concept. And high most of the time, higher software complexity often leads to an increased chance of having bugs or faults. So that's why we are, so you can see the keyword bugs, right? So that's why we are interested in learning software complexity in a testing course. So this is why we learned this course. So because software complexity is considered to be associated with like the chance of having bugs. most of the time. Okay, so now let's learn different complexity metrics. And let's start from the unit level complexity metrics. And unit level means that we care only about within what's happening within a function. The first complexity matrix we are going to learn today is called cyclomatic complexity. So the definition is like this. So it is calculated based on the control flow graph. And like we have learned control flow graph before, right? When we learn white box testing, right? And graphs, we know that graphs are made up of edges and nodes, right? So the calculation, since this complexity matrix is derived from this graph, so the calculation of this metric is by default kind of like associated with the number of edges and nodes, right? So by definition, the cyclomatic complexity is calculated like this. It is calculated by as E minus n plus 2p. And E, we can see is the number of edges, right? E. And N means nodes, right? So N is the number of nodes in the control flow graph. And P is the number of connected components. So because in graph theory, we have the definition of subgraphs. So a graph can have several subgraphs, and each subgraph is like a group of connected nodes, right? So P is like the number of subgraphs inside the larger graph. However, since we only care about a single function here, so we consider that everything is connected. So inside the graph, all the nodes are connected. Therefore, we just have the p-value equals to 1 for unit level cyclomatic complexity. So the equation could be simplified like this. So because the value of p normally equals to 1 here. So the equation is the cyclomatic complexity is the number of edges minus the number of nodes plus 1. So this is the formula used for unit level of cyclomatic complexity. And now let's take a look at an example of how do we calculate the cyclomatic complexity values. So let's consider this program here. So what do we need to do to calculate the cyclomatic complexity? Because it is calculated from the control flow graph, right? So we need to construct the control flow graph first, right? So let's try to draw the control flow graph. It is pretty straightforward. So we have we can omit the exit point here in this case. So we have an if statement here, and if the first condition is true, then we get to the second condition. And if it is false, we just return the value here. So you can see this is the control flow graph. And how do we calculate the cyclomatic complexity here? So remember the formula is E minus n plus 2. So let's just calculate this. So we have, how many edges do we have here? We have 4 edges, right? We have 4 edges. And how many nodes do we have? We have 5 nodes, right? So it is calculated as 4 minus 5 plus 2, and the cyclomatic complexity is considered to be 1 for this case. And let's think about what are the, like, why do we care about this? Like, what are the factors actually affecting the values here? Like, what are the factors in the characteristics of the program that could affect the complexity here? So So let's assume that if let's assume we just now we just mentioned, okay, the graph, we omitted the exit. So do you think by adding one more node here, for example, an exit here, increase the cyclomatic complexity for this original program? If we do this, let's say if we append another node here, will this cyclomatic complexity increase? The answer is no, right? Because according to the formula, it is E minus N plus 2, right? So we introduced exactly one edge and one more node. We are not increasing the cyclomatic complexity here, right? So as you can see, having more basic blocks does not essentially help us to increase the number of cyclomatic complexity. And let's assume that instead of returning if we take the false branch of the second if statement, instead of returning, let's have a loop to go back to the start of the program. So do you think will this increase the cyclomatic complexity here if we do this change? So instead of exiting the program, we loop back. According to the definition of the calculation formula, this will increase cyclomatic complexity, right? Because it is E minus N plus 2. We increase the number of, we introduced a new edge without introducing a new node. So the cyclomatic complexity grows here, actually. So the answer is yes. So can you see what's increasing the cyclomatic complexity here? So more edges, right? And more edges are often brought by branches and loops, right? So we can see each branch actually brings us two more edges and maybe just one node, right? And each loop here actually is bringing us uh, more edges without introducing new nodes, right? So cyclomatic complexity is actually used to capture the complexity of the program structure from the aspect of branches and loops. So you can also see from the name, it's cyclomatic. It's kind of like cycles, right? So we care about branches or loops. And let's continue. So assume we change the program into something like this. So if we changed the last node into something like this, so the does this increase the cyclomatic complexity here? So if we do this, no, right? And let's change the program furthermore. So so the difference is like instead of returning at each different point here, let's merge the two returns. So they will all be jointly returning here. So that this increase the number of the value of cyclomatic complexity here comparing to the previous one. Does this increase if we modify the program like this? Yes, right. So the reason is that we are merging the two basic blocks. We are returning and we are merging the two returns, like the two leaf returns are always like somehow like the leaf nodes inside the graph, right? And if we just merge the leaf nodes, we are reducing the number of nodes without reducing the number of edges, right? So you can see that what's affecting the cyclomatic complexity here? what is affecting the cyclomatic complexity here from the changes we just made. The returns, right? The returns are exits for the program because returns are like normally the leaf node. So they are somehow kind of special here. So if we can reduce the number of returns, we can have an increased number, an increased value of cyclomatic complexity. So you can see these are the factors that are affecting cyclomatic complexity. So some online materials, they just ignore returns if you search from online, but this is wrong. We should consider returns and exits. So here, because we know that okay, these are the factors that are affecting the cyclomatic complexity, right? So we can have a better way of calculating cyclomatic complexity rather than, like calculating it according to the definition from the control flow graph, because normally it could be very tedious to draw a control flow graph, right? So let's try this. Let's think about this. So the reason is that, just like I mentioned, constructing control flow graph could be very time consuming, and we can use the affecting factors to create a faster approach for calculating cyclomatic complexities. And the calculation formula is like this. So it is 2 plus if plus loops plus cases minus returns. So this is how it is calculated. So the reason is very simple. So if, like, for example, an if basic block, you can imagine it's introducing one node and two edges, right? So therefore, because we use E minus N, right? So it's adding one. So each if can add one to the final value of cyclomatic complexity. It's the same for loops. So for loops, we are looping back, right? And we need to go somewhere, right? So we have some structure like this. So we have a structure like this. So this is the exit point. This is the loop body, and this is the entering condition of loop. So for each loop, we can have like each loop is actually introducing one more edge. And it's very similar for cases. So cases are like, like we have cases are like we have cases are like ifs. So, but we will look at some detailed examples later about how do we deal with cases. So cases are like the branches under the switch, right? So each switch, like each case is like an if here. So that's why we plus one for each case. And the reason for minusing return is that because each return is, it's like connected with another. So normally a basic block is like this. It has an incoming edge and it has an outgoing edge, right? But for returns, it just have an incoming edge without any outgoing edge. So returns are kind of like consuming edges. So that's why we minus the number of returns. So this is roughly the rationale of why this formula is created like this. So let's take a look at this example again and see how can we use the faster way of calculating the cyclomatic complexity. So remember, the traditional way is to construct the control flow graph first, and just now we just calculated the cyclomatic complexity according to the control flow graph is 1, right? And now let's try to apply this formula here. So how many ifs do we have? We have two ifs, right? And how many loops do we have? We have no loops here. So it's 2 plus 2 plus 0. And how many cases do we have? 0, right? 2 plus 2 plus 0 plus 0 and minus, how many returns do we have? Minus 3, right? So it's 2 plus 2 minus 3, which is still 1. So it will give us the same result here if we apply this. So now let's try to do an exercise of how to calculate cyclomatic complexity with a more complicated example here. So let's try to do this. So we have a program like this, right? So what is the cyclomatic complexity for this program? So you are kind of encouraged to use the fast calculation here. But the question is, how do we deal with default for the cases, for the switch cases? How do we deal with this, right? If we try to apply the fast calculation. So do we consider it has 3 cases, or do we consider it has 2 cases here? We'll give you like 1 more minute to do this. So it's basically 2 plus the number of ifs, loops, cases minus returns, right? So how many returns do we have? And let's see the results. Actually, most of you have got it correct. The correct answer is 6. So let's see why it is 6. So if we draw the control flow graph, it will look like this. So as you can see, it is very, very complicated. And there are 15 edges inside this control flow graph. There are 11 nodes. So if we apply the formula, it is 15 minus 11 plus 2. So this is how we can calculate this according to the control flow graph. But if we want to apply the fast calculation here, let's try to apply this. So what are the number of ifs here? So we have 2 ifs, right? So we have 2. So how many loops do we have? 1, right? So the key is like how many cases do we have? Does default count as a case? Default doesn't count actually. Let's see why it doesn't count later. And how many returns do we have? We have 1, right? So it is 2 plus 2 plus 1 plus 2 minus 1, right? So it is 6. So we can see that we don't count default. We didn't count default as a case. Why? The reason is that imagine we have one switch block. Let's consider this extreme case. So imagine we have this one switch block without any case. Without any case. It just has a default inside this switch statement. Then there's no branching inside this switch block, right? This switch block essentially becomes just one single big basic block. So that's why only the cases, new cases are bringing in more edges, more branches. So that's why we don't count the default case here, although it is somehow considered as one of the cases for the switch statement. But because it doesn't bring in more branches, so that's why we don't count default in this formula. So case are just strictly like the case statements inside the switch block here if we apply the fast calculation formula. So that is all about the calculations and definition of cyclomatic complexity. We can see that because we have this fast calculation mechanism or formula, we can actually quickly calculate the the cyclomatic complexity of a piece of code by just doing some string matchings, right? We can match the statements. We can just go through the uh, code statement by statement and do a string match to apply the formula to calculate the cyclomatic complexity. So it is very fast. It could be very calculated very fast, and it is still very useful because it can reflect the complexity of the branches and loops, right? But there are some limitations for cyclomatic complexity. So it is often considered is a very typical approach for and widely used approach for calculating software complexity, but it is often considered as an oversimplification. The reason is that because we just care about the number of ifs, loops, and cases, right? But we didn't look into the actual conditions used inside the ifs, right? Actually different, all the ifs, loops, and cases can be considered as decision-making statements, but not all of them are equally complex, right? Because of the conditions inside these statements, right? So, for example, let's think about this program here. So this program is actually an implementation of the is a triangle function. So we can see that if these three conditions are satisfied, we can return that okay, these three values can form the three edges of a triangle. And if not, if any one of them is violated, then these three values cannot form a triangle, right? So the control flow graph would be as simple as this one, and we can according to the definition, we can quickly calculate the cyclomatic complexity like this. So the function below here is the same implementation here as this one here. So you can see it's just instead of using a compound condition here, we are splitting this compound condition into multiple nested ifs. So in this case, the control flow graph is rendered like this, and we have an increased value of the cyclomatic complexity here. However, these two functions, we know that they are essentially the same, right? So this means that this example actually shows us a critical limitation of cyclomatic complexity. It only measures the complexity of the control flow. It doesn't care about the data flow. So we just care about how complex is the structure, but we don't care about like what are the what's the data or what's the condition used inside the structures, right? So we don't, so this is a limitation of cyclomatic complexity. It actually ignores the actual content inside the basic blocks. So and also it actually ignores code size, right? Because sometimes we may have a very long function without any if, without any else, without any loops. We just have a very large function. And that very large function without any branch could have a very low value for cyclomatic complexity, but that very large function could still be very complex and vulnerable to bugs, right? So because of the limitation of cyclomatic complexity, let's think about another metric that can complement cyclomatic complexity. And this set of metrics is known as Halstead's metrics. So this is actually a person's name, and this is the guy who developed this set of metrics. And it was developed in 1977. It's a very old set of metrics. So during that time, people are like writing, they don't have, there are not that many high-level languages, programming languages like nowadays. There's no Python, no Java. Most of the time, people are writing like assembly code. And inside assembly code, we have operators and operands, right? So this, just because of this, so this, because it was developed in that, by that time. So it is actually dealing with operators and operands inside the program. So that's some backstories about this metrics. So just now we learned that cyclomatic complexity only cares about the structural complexity of the control flow graph. It doesn't care about the size, right? And Halstead metrics can help us to calculate the size, the complexity introduced by the size of the program. So it is calculated based on the quantities and of the operators and operands. So there are several key elements forming the different metrics here. So the first variable here is the number of distinct operators in a program, which is denoted as lowercase n1. And the second variable here is the number of distinct operands, which is denoted as the lowercase n2. And we have the total number of operators, which is denoted as uppercase n1, and total number of operands denoted as uppercase n2. So you can see that the uppercases are used for denoting the total numbers of operators or operands, and the lower cases are used for denoting the distinct number of operators and operands, right? So on the basis of these four values, Halstead defines some metrics. So the program length is denoted as the total number of all operators and operands, which is calculated like this, right? And the program vocabulary is calculated as the total number of distinct operators and operands. And program volume is calculated like this. It's n times log 2 n. So it's basically, this is considered as the program volume. And program difficulty is calculated like this. So you just need to know that, okay, it's calculated like this. And the programming effort for this program is calculated as the programming volume times the program difficulty. So by that time, because of the limitation is that of applying this Halstead's metrics is that we have to somehow identify operators and operands from a piece of program, right? You can see everything, all of the formulas are calculated with these four values, right? All of them are based on these four values. And these four values are strongly related to how do we identify operators and operands, right? So ideally, this metric should be language independent, but in reality, we cannot avoid some language features because in different programming languages, we may consider uh, we may consider the we may map the different notations inside the programming language as different operators operands accordingly. So let's just learn about the rules for C program for C language. So the identifier and function declarations of C programs are not considered here. So they are neither like they are neither. So if we just define a value actually without actually assigning any values there, so we just don't consider them. Or if we just declare a function prototype, like in a header file or at the start of a C file, then we don't care, we don't consider them as part of the metric, so we don't calculate them. And all the variables and constants are considered as operands. And global variables like so because we also need to calculate the occurrences of different variables, right? So if there are some global variables used in multiple places, it is considered as like just one occurrence because there's only one existing variable in the program, right? If we make it a global variable. And local variables are like considered the same in different with the same name in different functions are considered unique operands, right? Because each function is holding a different piece, like of value there, right? Although they may have the same name, but they are actually different variables, right? So you can I'll just skip like going through all the metrics here. So this you can just refer back to this slide for like how do we determine like operators and operands in C program. So you don't have to memorize all these. You just need to, like know, okay, it is in this slide here, and you can refer to this slide. And for exams, if you are encountering this, you are allowed to bring a piece of cheat sheet to the programs to the exam, so you don't need to worry about memorizing all these. So you just need to know that, okay, it is here, it is documented in this slide. So I will skip going through all the rules. And let's have a look at a concrete example to apply Haussteid's matrix instead. So let's consider this piece of code and try to calculate different values for Haussteid's matrix. So we know that all the different metrics, all the different rules are calculated based on these four different values, right? So now let's try to identify so let's try to deal with the operators first, and then deal with the operands first, and deal with the operands later, okay? So the operators are like somehow like the actions, right? So the actions inside the statements, right? So what is the first operator of this program? The first operator is the if here, right? This if is the first operator. And what is the second one in this program? Is the smaller than, right? And we have this plus equal, we have minus equal, and we have this equals, which is to assign values, right? We have this modulo, right? And since this assignment has been used, we just count it as a new occurrence of this, but it is not a distinct, unique operator, right? Because we have already included equals here. And this divided by is another one, right? Again, this assignment is just a new occurrence, right? And this plus here, and this plus is another occurrence. This times here, and this divide is just another occurrence, right? And plus, plus, divide, divide, plus, they are all repeating, right? So you can see that these are all the operators we have. And the total number of distinctive operators we have is like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we have 9 distinctive operators. And because some of them are occurring more than once, they appear in the program more than once. For example, the assignment, right? So we also need to count the number of occurrences for each distinct operator. So for if, like how many occurrences do we have? Just one, right? Like for maybe for plus, for this assignment, for equals, how many occurrences do we have? We have 3, right? So we can then count through the program to calculate all the occurrences of the operators. And if we sum them up, it will give us the total number of operators inside this program. So the uppercase N1 is 21 here. And now let's consider the operands. So the operands are the values involved in these calculations, right? Used by these actions, right? So let's count how many, let's go through the program to check for the unique operands. So I'm is the first one, right? 3 is the second one. And 12 is another one, right? Because I'm here is just another occurrence of I'm here, right? And Y, and then 1. And because this is like this int here is just like a type notation here. We don't count it as anything here. So K is another operand. Y is like repeating the previous one, right? And then 100 and J and then Y and 100 are repeating. So day of week is a new one. D is a new one. And M was repeating, was just another occurrence, right? And 26 and 10. And K is like repeating the previous one, right? And 4 is the first time we are encountering this operand here, right? And J is just yet another occurrence. 4 is like just repeating here. And 5 is a new one. And J is repeating. And 7 is a new one, right? So what we can get is something like this. And in total, we can have 15 distinct operands. And similar to how we calculate the number of occurrences for, yeah, this is 3142. So similar to how we calculate the total number of occurrences for operators, we can also calculate the number of occurrences for different operands, right? Because some of the operands are appearing more than once inside the program, right? So we can also count the number of occurrences for all the operands here. And this is what we can get. So now we can get the value of uppercase N2 is 25. So now we have all the four values of N1, N2, and uppercase N1 and N2, right? So now we can apply the formula to calculate all the different values here. So for program length, it's very straightforward, right? It's just the total number of all the occurrences of operators and operands we have, right? And in this program, the program length is 47. And program vocabulary is just calculated as the number of all distinct operators and operands, right? So the total number in this case is 24. And program volume is calculated like this. So it's just defined by house type. So it's calculated like this is 215.49. And the program difficulty is calculated like this. So basically, the larger number of operands we have and the more operators we have, the more distinct operators we have, the more difficult the program is considered to be for coding. So program difficulty is calculated like this, and the value is this. And programming effort is calculated like this. So, and based on these basic metrics, house type define some additional metrics for complexity, and which I think is not doesn't make too much of sense here today, especially when we have AI like our large language models. So the time required to program this piece of program according to the calculated values is calculated as t, and which is e divided by 18 seconds. And the number of delivered bugs or estimated number of bugs inside such a program is considered as V divided by the program volume divided by 3,000, or this one here. So if the actual bug detected in the program, the number of the actual bugs is smaller than the number of estimated bugs, then in the program quality is considered as kind of acceptable. But I don't think this makes too much sense, because if we come back to the previous example here and apply the two new metrics, you can see that the time required to program this piece of code is considered as 87.78 seconds. So you can imagine this piece of code is actually used for calculating on the day of a week, given the month, year, and the month and year and actual date. So this is not very I think it will take definitely more than 87 something seconds to code this, right? So I don't think this is like the case here. Maybe by the time when Hofstad designed these metrics, maybe this is the case, but now it's definitely not. And if we code with AI, then everything is determined just mainly by the length of your input prompt and the length of the output tokens, right? So it doesn't matter. So only the size of the program matters here nowadays. And the number of delivered bugs expected for this program is calculated as V divided by 3,000, and the value is 0.07. Because it is value smaller than 1, so it means that if we having no bugs inside this program is acceptable. Having one bug is not acceptable. But you can see that here in this program, it has a very complicated case here. So I don't think it makes sense as well. So that's why I just call them additional metrics. So we don't need to we don't need to memorize everything here. We don't and then we just use these two values as a reference. So it's not the case in reality. So now we have covered unit level complexity. We learned two different family of metrics, right? We learned cyclomatic and complexity, and we also learned Haussteid's metrics. So cyclomatic complexity is more about the structural complexity, and Haussteid's metrics is more about the program volume, right? Or the complexity introduced by the size of the program. And before we move to the integration level of complexities, let's have a 10 minutes break, and I'll see you at 4:06. Okay, let's continue. So just now we learned different metrics for unit level of software complexity, and unit level means that we only care about the complexity within a function. However, we know that functions inside a piece of software can have interactions with each other, right? So now let's think about the integration level complexity, which are dealing with the interactions between different functions inside the program. So the first one is the cyclomatic complexity for call graph. So you can see here, okay, so we have a new type of graph here, which is called a call graph. A call graph is actually a special type of control flow graph. So we have learned that control flow graphs are made up of like all the graphs, all the graphs are made up of edges and nodes. In control flow graph, the edges uh, uh, used for are used for describing the flow of the execution across the nodes, right? So in a call graph, um, the function of the edges are similar, so it's also used for denoting the flow of execution of the program. However, the nodes are different. So in a normal control flow graph, each node is actually a basic block made up of statements, right? And in a call graph, each node is made up of a function. So here, according to the definition, so each node in this graph represents a procedure or function. And so procedure is just like a formal name for function in program analysis. And each edge is just indicating that there's a calling relationship between the two nodes. So if we have an edge pointing from node A to node B, it means that function A is calling function B. So this is the definition. So, oh, I forgot to add the animation here. So let's consider these functions here. So let's assume that we have a calendar function as the main function. And this calendar function calls get date, zodiac, next date, memorial date, weekday, and Friday 13th. And then get date will call get digits and so on. So this is the calling relationship among these functions. So according to this, we can build a call graph like this. So which is very straightforward. And And the advantage of having this call graph is that we can quickly identify the relationships among these functions, right? Because here we care about the interactions among these different functions. So if, let's assume that is leap is implemented wrongly or there's a bug in this is leap function. So which other functions may fail because of this bug? We can quickly identify, right? So the colors of its leap will be affected, right? And according to, if we want to get the colors from this, something like this, it's very tedious, right? It's very tedious. But inside a graph, it's very straightforward. So its leap, if its leap is wrongly implemented, we can clearly see that the day number to date to day number, and last day of month will be affected, right? The colors, the direct colors of its leap will be affected. So this is the advantage of having this call graph. And since we have a graph, we can apply the complexity metric we just learned that could be applied to graphs, right? And can you quickly tell me what is the complexity matrix we just learned that can be applied for graphs? It is indicated in the slide's name, right? It's cyclomatic complexity. So we can quickly calculate. We can also calculate cyclomatic complexity for call graphs. And for this graph, according to the definition, it is calculated like this. So we have 19 edges. We have 15 nodes. So the total number of cyclomatic complexity is 19 minus 15 plus 2, which is 6. So this is call graph. And there are some other concepts associated with this calling relationships. And the first one is fan-in. So fan-in means for a function, the value of fan-in is how many functions are directly calling this function. So directly call means it's not an indirect call. And there are some cases for indirect calls. For example, if we just call a function through a function variable, right? We can also, in C programs, we can also call functions with function pointers, right? So a direct call means we are just invoking the function directly without using like any function variables or function pointers. So this is to simplify the analysis process. So let's consider this example here. So let's try to go through this example and go through the functions one by one. So for sleep, what are the direct callers in this example? Can you quickly tell me what are the direct callers? So the callers are last day of month, date to day number, date to day num, day number to date, right? These 4 direct callers. Oh, I think I omitted one here. Oh, sorry. These two are the same. These two are the same. So we have 3 direct callers, right? And therefore the fan-in is 3. So let's try one more example. Weekday. So for weekday, what are the direct callers? So the direct callers is Monday and is Friday, right? So we have 2 direct callers, and the value of fan-in for weekday is sorry, we have 3 because it's also directly called by men. I just forgot this one here. So we have 3 direct callers, and therefore the fan-in is 3. So similarly, we can calculate the fan-in values for all the other functions, right? So the fan-in is just how many callers are there for a particular function. And in comparison, we have the fan-out value. So fan-out value means how many functions are directly called by this function. So you can see directly call also means we just care about one layer of calling relationship. So if A calls B and B calls C, and A never calls C directly, so we just don't count A to C as a direct call. So let's consider the functions according to this example here. So for the calendar function, like what are the direct callees? So we can see get date, zodiac, next date, memorial date, weekday, and Friday 13th, right? So we have 6 callees, and therefore the value of fan-out is 6. And you can use the rest of the functions as a practice, but it's very straightforward. So you just call the number of callees and that is the value of fan out. And for some functions, they are the like in the leaf node um, of the calling graph. So they have no callees, and therefore the values are of fan outs for these functions are just 0. So with the fan in and fan out relationship, sometimes we can build a butterfly graph. And the butterfly graph is like a particular pattern or particular shape inside a call graph, where a function can have many uh, callers and callees. And this function in the middle, having those many callers and callees, is known as the shared core. So why do we care about this? The reason is that a butterfly shape means there is an important integration point inside the program because we have like a lot of colors for this shared core, right? And we have a lot of callees of the shared core. So this means that this shared core is an important integration point. And therefore, this shared core may need careful tests. And we will learn about these different tests later on. And this is a typical shape of a butterfly shape in a call graph. You can see that this one means the shared core has fan in because there are many features calling this shared core. And this core has a very high fan out because it is used by, it actually invokes many helper functions, right? And this could be, and if there's a bug inside this shared core, it may affect all the features and it may also affect the helper functions, right? So therefore, this is an important point for us to analyze. And because you can see this graph here looks like a butterfly. So it is known as a butterfly shape or a butterfly graph. So this is a special pattern in the call graph. So just now we learned, okay, we can extract different complexity metrics, like based on the calling relationships among these functions, like based on the call graph, and we can identify important like integration points by identifying the butterfly shapes, right? So now let's think about the integration complexity from another angle. We have learned object-oriented programming, right? And there are actually also some complexity metrics for these object-oriented programs. And this the most famous set of metrics for calculating the complexity for object-oriented programs is known as the CK matrix, which is also named after the inventor's name. And it like Hausteid's matrix, is a set of complexity metrics that could be calculated with some with some values extracted from the software. So it is actually made out of 6 different metrics, and these are the 6 metrics. So most of the metrics, the calculation method are actually explained by the name. For example, weight methods per class is actually just summing up because we know that each class can have a lot of methods, right? So the weight complexity of weight methods per class is just the sum of the complexity of each individual method inside the class. And we can use cyclomatic complexity as the complexity for each method here, right? We can use the unit level complexity for each method and then just sum them up and it becomes the WMC. And the depth of inheritance tree is just like because each class can have some inheritance structures, right? So it's just the depth of the class inside that inheritance tree, right? It's very straightforward. And the number of child classes is even more straightforward. We just need to calculate or just to count the number of child classes inheriting this class, right? And for object-oriented programming, there's a very well-known concept called high cohesion and low coupling, right? So we want the design to have high cohesion and low coupling, which means that we want the features to be self-contained and we want the features to be modular, right? So we have two metrics related to the coupling and cohesion. So coupling between classes is calculated like this. So it's calculated like as the number of shared function calls or number of variables shared by different classes. So if the two classes are sharing more variables or they are calling each other via the method calls, then the coupling between these two classes is considered to be strong, right? And the cohesion here is more complex. So we will introduce this in the following slide. And the response for class is like, it's just by adding the response for class is just calculated like this. It's just by adding the number of methods in the class plus the number of distinct method calls made by the methods in the class. And this is, and you can see an example there, but you can see an example by clicking this link here, but we won't go through the details here. And because low coupling and high cohesion is the most important concept for object-oriented programming. So let's introduce CBO and LCOM in detail in this class. So let's continue. So in order to calculate LCOM, the cohesion of the methods inside the class, we need to know like if the methods are actually sharing some information inside the class, right? Like how closely are they working with each other, right? So what you can do is the first step for calculating this lack of cohesion on methods is we need to identify methods and attributes first. So we need to list down all the methods and attributes of the class. And then we determine the method and attribute relationships, which means that we try to identify which attribute is used in which method. So this is the second step. And the third step is we evaluate method pairs. So we check for each method, for each pair of two methods inside the class, we check whether do they share some common attributes or not. And then we can calculate LCOM. So we can calculate the number of method pair. What we do is we just use the number of method pairs that doesn't share any attribute minus the number of method pairs that share at least one attribute. And this could give us sometimes this because we just use one value to minus another value, right? This sometimes could give us some negative values. And if we get a negative number, we just set the value to be 0. So this is the calculation of LCOM. And let's take a look at an example of how do we calculate this. So remember, these are the 4 steps. So the first step for us is we need to list all the methods and attributes of the class, right, for this given class. So what are the methods here in the class? So we have three methods, right? We have M1, M2, and M3. And the attributes are A1, A2, and A3, right? So these are all the methods and attributes. And the second step is that we need to decide which attributes are used in which methods, right? So in this example here, M1 uses A1 and A2, right? And what about M2? M2 uses A2 and A3, right? And M3 uses A3, right? This is the second step. And the third step is we compare the pairs of these methods and see if they are using the same attributes or not. So how many pairs do we have for this example class? We have three pairs, right? We have M1, M2, M1, M3, and M2, M3, right? So for M1 and M2, we can see that they share A2, right? Therefore, they are considered as cohesive, right? M1 and M3, they don't share any common attributes, right? So they are considered as non-cohesive. And we have M2 and M3 sharing the attribute A3, right? So this is considered as a cohesive pair, right? And the last step is we just use the number of non-cohesive pairs minus the number of cohesive pairs. So what we got is we got one non-cohesive pair and we have two cohesive pairs. So the value is 1 minus 2, which is minus 1. Because it is a negative value, we need to set it to 0. And there are some variations of how can we calculate the lack of cohesion over methods inside the same class. And there are some different calculation methods flying around. So you can find a very good summary here in this link. And we just learned this one here in this course. And now let's think about an open question. Just now we learned how do we calculate the lack of cohesion on methods, right? So do you think according to the calculation or the name of this metric, is the value of LCOM the lower the better, or is the value the higher the better for a program? So to have a better quality, is it the lower the better or the higher the better? You need to think about the saying or the ideal case for object-oriented programming. So let's see those. Actually, most of you have got it correct. So it's the lower the better, because what we want is we want low, for object-oriented programming, we want low coupling, which means that the classes are modularized, right? We want low coupling. So, and we want the modularity because Because if we modify a feature inside a class, it will have less, it will affect fewer other classes, right? So, so that's why we want low coupling, but we want high cohesion, which means that the the methods that are like intersecting or interacting more with each other are grouped within one class, right? So we want high cohesion. And according to this value, this calculates the lack of cohesion. So if the higher the value is, it means that we are lacking cohesion, right? So the lower the, so therefore if we have a lower value of LCOM, it means that we have a higher value of cohesion. So that's why the value is the lower the better here. Okay, so now we have covered different metrics for unit level complexity and integration level of complexity. And now let's think about system level of complexity. And actually, there's for system level of complexity, it's very simple. We just consider it as an integration of all the components. So we don't care about like we don't care about how do we calculate a slice of the program. So we just use the integration of the entire program. So we can reuse the integration level of complexity, but just use it for all the components of the system. So it's very straightforward. And let's come back to the very first topic of we have learned today, which is why we learn software complexity. We know that, okay, it's somehow related to the number of bugs, right? So we know that, okay, we intuitively think that, okay, the higher the value, the complexity value is, the more the more buggy the program might be, right? So, however, there's a research in 2018. So it actually studied whether software complexity is positively related to vulnerabilities or bugs. So the result is very hard to tell actually. So this is the link to the paper. And this is a table from that paper. You can see that they have done a huge study of bugs inside many different programs. And they have tried a lot of detection methods for vulnerabilities, like all the different software, static analysis techniques, like all the different machine learning based like predictions for these bugs or vulnerabilities. And they also applied different software metrics like system level of software complexity metrics to see whether they can predict the existence of bugs. Remember, we have a prediction for bugs with house type, right? With one of the house types metrics. So they are using a lot more techniques to do this kind of prediction in this study. And the result is that most of the prediction methods, they cannot simply outperform the counting the code size. So basically, the the more lines of code we have, the more likely that there is an existence of a bug. So most of the prediction method, no matter how complex it is, no matter how like novel it is, they may not outperform like simply counting the code size. So so that's why although intuitively and in practice, actually a lot of companies are also calculating this software complexity, and they may have some restrictions for like cyclomatic complexity for each function you write. Like for some big companies, they don't allow you to write very complex functions, right? They encourage developers to break up complex functions into several smaller ones. But that's just an intuition. If we do a careful research, we may find that actually it is very hard to tell the relationship between software complexity and the existence of bugs. So this is the some insights from the research. And the relation of software complexity with testing, or we will be learning fuzzing later. So it's still another type of testing technique. So the relation is that although like I said, although the relationship between software complexity and the existence of bugs or faults is not very clear, we can still use it as a signal for identifying valuable targets within the program for us to test more. For example, this is a practical tool. So it can help you to scan through, given a large project, it can help you to scan through the project function by function and list down a prioritized list of functions for you to conduct testing. And you can see it calculates a vulnerability score. And this vulnerability score is kind of like a prediction of the existence of vulnerabilities. And inside this, you can see our old friend, cyclomatic complexity here. So complexity is still considered as like a useful indicator of bugs in practice sometimes. But the relationship theoretically is the relationship between the complexity and the existence of bugs is not very, we don't have a conclusion here until now. So that's all for today's lecture. And before we end, let's have a quick recap of what we learned. So as I'm going through all the concepts, you can try to recall what we have learned, because according to the theory of like memorization is the best time to repeat what you have learned after 20 minutes of learning it, or 20 to 40 minutes of learning it, right? So let's have a recall of what we learned today. So today we learned software complexity, and software complexity is different from computational complexity, right? Computational complexity is used for different algorithms, but software complexity is to describe the difficulty of writing or modifying or maintaining a piece of code, right? And we learn it because it is considered to be related to the existence of bugs, although some research tells us that maybe it's not. But in practice, most of the time, people still think that a more complex software is likely to be more buggy. So that's why we learned this. And we learned 3 different levels of software complexity. So the first level is unit level software complexity. And for unit level, we care about what's happening inside a function, right? And we have 2 types of metrics. The first one is about the structural complexity, which is known as cyclomatic complexity. And we can derive the value of cyclomatic complexity from the control flow graph, right? And the formula for calculating this is E minus n plus 2, right? And E stands for the number of edges. N stands for the number of nodes. So we just use the number of edges minus the number of nodes plus 2 as the value of cyclomatic complexity. And because sometimes it's very tedious to draw the control flow graph, so we have a faster approach for calculating this, right? And this faster approach is derived by identifying which factors can affect which factors or which type of statements inside the program can affect the final value of cyclomatic complexity, right? And we know that branches, loops, and returns are affecting cyclomatic complexity. So the formula is calculated as 2 plus the number of ifs plus the number of switch cases without default plus the number of loops minus the number of returns, right? So, and we also learned the rationale behind this because these decision-making statements are bringing in more edges and returns are bringing in more nodes rather than edges, right? So that's why we minus return, right? So that's the rationale behind this. And then we learned just using cyclomatic complexity could be very limited because cyclomatic complexity doesn't care about the size or the volume of the program. And to complement cyclomatic complexity, we introduced another set of metrics, which is known as Haushalts metrics. And for this set of metrics, complexity metrics, we are dealing with the number of distinctive operators and operands and the total number of operators and operands, right? And based on the four values here, we can derive several different metrics. We can calculate the program volume, we can calculate the program difficulty, we can calculate the estimated programming effort. And there are, of course, two additional metrics which can help us to calculate the estimated programming time and the estimated number of bugs, right, from Haushalts metrics. But those two values may not be practically useful as a reference. And that's all about the unit level complexity. And then we learned integration level of software complexity. So for unit level, we just care about what's happening inside a function. And for integration level of software complexity, we care more about the interactions among different functions, right? So to capture the interactions among different functions, we can build a call graph. Since we have a graph again, we can calculate cyclomatic complexities on this new type of graph, right? And there are some special patterns which are known as the butterfly shape inside the call graph, which means that there are some nodes which have high value of fan in and high value of fan out, right? You need to still remember what is fan in and what is fan out. And these butterfly shapes are like very interesting points for us to test more, right, in the call graph. And we also learned about object-oriented some special metrics for object-oriented programs, right? So for these object-oriented programs, the key is we want high cohesion and low coupling. So can you still remember how do we calculate the cohesion within the class, right? We need to identify all the attributes. We need to identify all the methods. We need to see which method is using which attribute. And we need to check for each pair of method, are they sharing some attributes or not, right? And we use the number of method pairs that doesn't share any attribute minus the number of method pairs that share at least one attribute, then we can get the value of lack of cohesion over methods, right? And for this value, because we want high cohesion and low coupling, the lower the value of LCOI is, the better the quality of the software is, right? So that's all about the integration level of complexity. And for system level of complexity, we know that, okay, it is actually just, and we can just consider it as an integration of all the possible components inside the program. And that's that gives us the system level of complexity. And we know that although in practice people think that okay, complexity is positively related to bugs, but in some very rigorous research, we know that it may not be the case. So the relationship, the actual relationship between software complexity and the existence of bugs is kind of unknown until now. So that's all about this. And thank you for coming to today's lecture, and have a nice weekend.